So I think pretty much everyone has seen this video by now. This is Sora from ChatGPT's author, OpenAI. From a text prompt, it can generate a video that I can't even tell apart whether it's AI generated or reality. I mean, this is not reality, I know, but this is so cool. It could have done by an artist. So I think, like many of you, we want to understand how that could happen, right? How that's being made, how the model can be tuned to be such performant. So the first question I'm asking is, before an AI can create a video, how does it perceive a video first so that it can understand it and then recreate it? So of course I looked at the technical report released by OpenAI, and the key element they have been referring in their technical report is patches, space-time patches. Of course, when I go into deeper, it showed a few references, how they were doing the patches, and there are 4 papers being listed. The Vision Transformer paper is probably well known, the MAE paper is probably well known. I would like to dive deep into the 2 papers they referred over here. One is called ViViT, Video Vision Transformer, and the other is NaViT, or Patch and Pack technique, which is, I think, a native resolution video transformer. So, before going into ViViT and NaViT, I want to do a very quick recap on what ViT is. ViT stands for the Vision Transformer. I think it was created to replace CNNs to become the state-of-the-art model for computer vision field. So before, when we were trying to let a computer to understand an image, we were using convolutional neural nets, or CNNs. We're assuming that the vision is sensitive to the local receptive field. What that means is, if we have an image, we're going to, this is the image over here. We're going to represent the image as zeros and ones and floating point numbers, RGB channels, of course it's a computer. And what we do is we look at things locally and we detect features. Maybe there is a line that's horizontal over here. Maybe there is a line that's 45 degrees right next to it. And maybe if we pass these little features down to the next layer, then maybe we'll see maybe there's a circle over here. And then later, because of a circle, the different shadings, maybe there's an eye over here. And eye detection, maybe the eye nose becomes a face over here. And when it's a face, it has 2 eyes, it has furry skins. Then the model is not very difficult to understand that it's a cat, it's a dog, it's a face of a person, things like that. So this is how people used to do it. The next thing that came into play is, because CNN has this local receptive field, and we know that may not be true. For example, I don't know, just imagining a photo of someone throwing a frisbee and the dog is looking at someone. The dog's attention span may not be localized. It may just be looking at something very far away. So the local receptive field is useful, but has some limitations. The inducive bias is causing some limitations to the CNN itself, which is also the same reason that it's making it so efficient. So the transformer then was introduced. The concept of a transformer in natural language model is that a word will be looking at not only its neighbors, but all different words in the sequence and decide which word it's going to pay more attention to. So converting to video, this is what that means. We have an image and we are going to break it down into many little patches right here. There's a upper left patch, there's lower right patch, there are all these patches. And we are going to linearly project those patches into tokens, and which is just, it's like a word, right? A token is a word. Then we're going to go through the transformer encoder, which is going to look at the relationship between this patch and every other patch to ask, hey, are you related to me, and what about you? And they ask all kinds of questions, and they combine the context information together and output it at the end of the encoder. Of course, before classification, they pass it to the MLP head fully connected layers to output the class. So this is the key. And if you look at what's in this model, it's exactly the same thing we have seen that's used to process languages. It's the patches actually plus the positional encoding, because if we just put those patches in, we don't know where this patch is within the whole image. And this is important for image understanding. So we're going to add a positional embedding. This is the first patch, second patch, third patch, etc. And we put them together. We put it into the standard transformer block, which some of you might be familiar if you haven't seen the transformers in natural language processing. It's putting all those embedded patches, which is just a set of vectors. It passes through layer norm to normalize it, and then to put it into multi-head attention, which are QKV pairs. Pretty much Q is asking a question for each patch, and K is detecting if that question being asked by some other patches is related to myself, right? So, and QK is basically a query and key. Once they find a match to say, well, this patch, I'm related to you and I'm answering one of your questions, and then they multiply it by a V value in the V matrix, and they use those method to, I would say, contextualize the token, such that the token does not only contain the information of itself, but also the upper or lower context surrounding that patch. And later, the original input was added again to the output of this multi-head attention block, because you don't want to see vanishing or exploding gradients. And then we go through another normalization, another multi-layer perceptron, just to project it to the, I would say, semantic space of our interest. And then we just added them together. And then we repeat it multiple times, L times over here, and that's the transformer encoder. So this is the basic idea of the ViT. So that is a very brief history of how we're coming from CNN to a transformer, a vision transformer. But the vision transformer is only dealing with static images. Now we have videos. What do we do? It's the paper ViViT that I was looking into. It's actually a very simple idea if you just look at it. Well, for images, we have two dimensions, right? We have the width and the height, which is width and the height over here. That's only two-dimensional. Now we're just having another dimension called time. So we're essentially dealing with 3D data. And instead of doing a patch that's 2D, we're going to project this 2D to 1D anyway, right? Instead of projecting 2D to 1D, we just have a cube that's 2D in space and 1D in time. And the authors are calling them the tubelets, I think. It's a tube, right? Which project the 3D into 1D, and we run transformers on top of it. That's pretty straightforward, right? Then you must say, well, isn't this just trivial? Why don't people do it before? Well, previously people have been, of course, doing video understanding, and there are a lot of methods to it. I think, arguably there's this very elegant method called optical flow that I was looking into. What this does is the whole model has two towers. The input video were split into two channels, right? The first channel is about spatial stream. They look at the spatial video to understand whether there's a person in it, whether there's an arrow in it. This is pretty standard, just CNNs. And the other is focusing on the temporal component of the flow, where they are looking at the trajectory of the hand moving. Are they moving up? Are they moving down? What are their X and Y components? And these two separate convolutional neural network only combines at the end and predicts a class. And I'm going to go deeper in this temporal stream component because you use something called optical flow. Optical flow is pretty interesting. If you look at these two frames of the image and we focus on those green little boxes, what's happening is that person is trying to pull out an arrow. And that pulling moment, if you zoom in, is a hand moving upwards to the right, right? So you can see all those intensity of the velocity, and you can use those information. And this method works very well. You might say, hey, why don't they use the method you were talking about in the previous slide directly? Well, they actually tried, right? They actually tried to put them on the convolutional neural network. This is not going to be the focus of this note, but you can see that it's a paper I found a while ago called A New Model in the Kinetics Dataset. This is actually something they considered. It just doesn't work very well using just a 3D ConvNet. They also tried LSTM two-stream model, which is what I just mentioned, and a fancier version of two-stream, and the two-stream 3D ConvNet. There are many different methods that we just talked about. Actually, what I talk about is not the two-stream model. It's a more complicated version of the two-stream model over here. And we have the transformer, and that's what changed the whole game. So, how do transformers do? So this is something I've been taken from the paper, that they have all those tubelets they extracted, they embed them to tokens by linear projection. And then we have the token embedding, and they added positional embedding. I am pretty sure they also meant to say this is also temporal embedding plus all these. And they pass these to a standard transformer block, which is seen on the ViViT, right? It's pretty standard. That's the same thing. So this should work pretty well. Obviously, the authors found some issues in them, and they only called it the model number 1. Why is that? Because this method, if you think about it, let's say I'll draw this matrix. I'll just say this is a 3x3 matrix, and I'll say actually 4x3. Actually, this is the spatial axis. I have 2 patches, and this is the time I have 3 patches. If you do this method, then every patch over here, let's call them 0, 1, 2, 3. And if I may call this 4, 5, 6, 7, then patch 0 is going to look at its attention with 1, with 2, with 3, with 4, with 5, with 6, with 7. So it's going to look at all the patches. And therefore, the computational cost is going to be quadratically proportional to the number of patches we're having over here, which is very expensive. We have more computational powers today than before, yes, but this is going to be too expensive. Maybe we can find cheaper methods. So the authors proposed method number 2 called Factorized encoder, number 3 called Factorized self-attention, and number 4 Factorized dot product. Let's go into it and see what each of them means. But something you can keep in mind is all the latter 3 methods are created on top of number 1 to reduce computational cost. So this is the method 2, the factorized encoder. So what it does is, instead of just doing the attention on space and time altogether, it's going to look at all the encoders for spatial first, and then look at all the encoders on the temporal component second. So what it means is, to my understanding, and please let me know, because I checked some of the raw code online to understand this. If my understanding is different from yours, please leave a note and let me know. So again, we have our examples. Let's say this is spatial, this is temporal. What could happen here is, first of all, we're looking at every time, well, not frame, but time blocks, right? For every block, we are going to look at the spatial attention only. I'm only going to look at attention across all the neighboring tubelets or neighboring patches, embeddings at the same time as happening together with me. So this first encoder only deals with the spatial information. And after that, I'm going to have some new tokens with enriched contextualized information. And then what I'm going to do is I'm going to run another attention that's going to be temporal. And in that step, I'm not going to look at other locations. I'm only going to look at my location, because this location is already re-enriched with neighboring context from the first encoder. Of course, I'm going to also prepend the class token before me, and I'm going to look at all the temporal interactions. And after that, I'm going to pass all of those information to the MLP head for the classification. So this is looking at all the spatial information together. After that is done, look at the temporal information. This is done by 2 steps, and therefore it decreased the computational cost a lot. As you can imagine, this is a decoupled method. The third method is similar to the second method, that is going to look at spatial and temporal in a decoupled manner. But what is different here is that instead of looking at all the spatial component and put all of that to the temporal component and output, it's going to look at spatial, temporal, spatial, temporal. So basically what's happening is in one of the transformer block, it runs 2 attentions. The first attention block is only spatial. The second attention block is only temporal. So basically, instead of cleaning up with all the spatial and do the temporal, it's doing spatial, temporal, spatial, temporal. Actually, the author did some ablation study, and they realized that even if you swap the spatial and temporal block orders, if you run temporal first, spatial second, that doesn't really matter. So this is going to be roughly the same computational cost with the method number 2, but it's going to have more parameters because we do have this extra attention calculation. The fourth method here is not even thinking about doing spatial first and temporal second repeated. They're saying, well, can we do it simultaneously? And how they did that is when we were doing the self-attention block, in every of the multi-head dot product attention, we do spatial heads and the temporal heads at the same time. Remember, we have those KQE that we're going to ask questions and find the keys and find the value. What we're going to do is have 2 sets of heads. Half of the heads are going to be used for the spatial queries. The other half are going to be working on the temporal queries, and they're going to end up with 2 sets of tokens that's going to be concatenated together. And the first part is only spatial context, and the other part is temporal. So with this method, they're doing them simultaneously. And it's also reducing the computational cost because it's also doing spatial and temporal separately rather than them coupled. So all those methods, I think, to me, makes a lot of sense. Let's see. I think the author did the study to show what the result is. Let's find out. So here comes the result. In terms of accuracy, actually, the first model is actually here. This is blue is number 1, the red is number 2, the green is number 3, the gray is number 4. The accuracy, the first one is the best. Of course, it has the most computational cost to it, right? If you look at the computational cost over here, at the same tuplet size, 16 by 2, is here the input tuplet size. It's also the most expensive model, and the performance is the highest. It's actually more than a performance issue. It's also going to cause overfitting issue when the sample size is not big enough. So therefore, the author said, yes, although it's most accurate model of the all, it's probably not the model they actually are going to follow up to study the most in the remaining of the paper. The model that actually they chose to study the most is this method. It has slightly lower accuracy than the model number 1, but the computational cost is almost the lowest. This is the model number 2, the factorized encoder. If you don't remember what that is, the factorized encoder is the model where they did all the spatial encoder first, and then they do the temporal encoder, and they just put all of those tokens after processing to the MLP to get the class. So this is the result. I think it's really interesting. I was almost thinking that the force model, because they always look at space and time at the same time, it would be the best. Actually, the performance is actually the worst. So that's how I understand videos, and just taking a look at those videos generated by Sora. It's pretty cool, right? But hold on. How come those are different resolutions, and how do I adjust to that? So with different resolutions, there are obviously ways people have thought about. Can we just make all the sizes consistent? This is a medical image I found from a paper in 2023. And they say, well, you know, this is, I think, an image about breast cancer. Can we just make it all the same size by resizing it? Well, obviously it's going to work, but at the same time, it's going to distort the image in a way that is going to stretch it out of its original aspect ratio, and that sometimes changes the semantic meaning, in the image, right? So that's maybe working, but decreases accuracy. Well, what about padding? Or just padding all these black areas? Then, of course, this is going to work. And it will not impact accuracy because the model can probably learn that it's padding. But the problem is it's going to be a little bit wasteful. It's going to still calculate all the weights over there, and it's not going to be helpful. So what do? Thinking about it, is really difference input size a new problem in machine learning? Probably not. Of course, if you look at computer vision, ImageNet, for example, most of the images are not square, and if you look at the distribution, there's a wide distribution of all the different aspect ratios and resolutions. But it's also a problem for NLP, right? For example, if you look at all the different data sizes, none of the sequences, a sentence, of course, there's no guarantee 2 sentences are going to have the same size. And what people have been doing is they're packing it into the same sequence. It's called example packing. What they do is, maybe this is a long sentence, it'll take a message of itself, or it'll take a sequence of itself. This is a set of 3 shorter messages, and they can pack to be a long sentence. And this one is 2 sentences. We don't have enough space to pack the 3rd short sentence, so we'll just have a few padding tokens at the end. They're still padding, but at least not that expensive. And they have ways to deal with all the self-attention to make sure within one sentence it's only going to still attend its siblings in the same sentence rather than cross-attending into other sentences. So there are ways to do that. And obviously NaViT, which is the second paper we're going to talk about, the patch and pack NaViT, native resolution vision transformer, I believe, did the same thing. They just packed all those images over here. Within one sequence, we have image 1, image 2, and image 3. And of course, there will be some padding. But just make sure when they are doing pooling, if they need to do pooling, I think in some of the model variants, instead of doing a classifier token, they used attention pooling to get the classes. So when they're doing pooling, they're going to have different pooling tokens within that sequence of itself. Or self-attention. They have self-attention only querying the siblings in its own sentences. And data preprocessing, when they're dropping tokens, they first patchify, and then when they drop tokens, they drop at a probability of all of these. The benefit of that is actually in the training data, you can see different ratios of dropping rate naturally in the training set itself. So that's what the NaViT paper did. So how does it work? How well does it work, actually? It's actually working very well. Just, even beyond supporting native resolutions, it's more efficient. If you look at this, this is the pre-training accuracy versus training cost. This is the fine-tune accuracy versus training cost. You will see that at the same accuracy level, it's basically 4 to 5 times faster when you're packing multiple examples into one sequence versus just, having a fixed sequence. And of course, and this happens both in pre-training and training. Or in other words, with the given cost, the model can be much more performant in the packed methods. Also, it's very convenient over here that the x-axis over here is the inference cost. The y-axis here is the accuracy. So it's making the serving much more convenient and continuous. What I mean by that is, well, if you have a super expensive model like this one, yes, it can have high accuracy at a very high computational cost. Or you can downsample the image. Maybe you can have the model to be cheaper, but the accuracy drops drastically. With the NaViT paper, what you can do is you can have a very continuous curve because it's natively supporting different ranges of resolutions such that you don't have to choose a different model. You can have the same model to deal with all different resolutions, and that's a huge benefit. You can do the trade-off at a continuous spectrum. There is one challenge we need to solve over here, which is how do we do the position embedding? So in the traditional ViT, let's say, because everything is the same resolution, it's much easier, right? We have 1, 2, 3, 4, 5, 6. So we just say, I'm embedding the patch number 1, number 2, number 3, number 4, number 5, number 6. But if you have different aspect ratios, you have different resolutions, then the number 4 in something could be right below number 1. And in other cases, number 4, for example, over here, would be, quite far on the right than the number 1. So to deal with this problem, the author decided to do X and Y differently, or separately. X is from 0 to 2, Y is from 0 to 3, and what they're going to do is they're going to find X embedding, Y embedding, and then combine them together. How do we combine? You can do addition, you can do multiplication, there are different ways, but the core is we do them separately and then pull them together. So this is one way. And this is using the absolute coordinate method. This method also has its own flaws. For example, we have 0 to 2, I have 0 to 6. What if the next time I have a big image where the x-axis could be as high as, 15? Then we're extrapolating our embedding, right? And this could be a problem. So how do we deal with that problem? One way to deal with this problem is just that we cap the max coordinate at 1.0 or 100%. So whatever we do, we won't have maxing out or extrapolation of the coordinate embedding. This is working very well, right? But there is one tiny problem, which is, it's not preserving its aspect ratio. The x-axis 50% to 60%, let's say, could be quite longer than the y-axis 50% to 60%. So this aspect ratio is not preserved. Is this a problem? We don't know. Is there a method that we can fix this? So one thing we can do is, why don't we just find the max edge length to be 100%? For example, this picture is wider than taller, right? So we're going to just say this is 100% on the x dimension, and the y dimension max is just 71%. So this is also a method that's not having extrapolation problems, but also is preserving the aspect ratios. So the authors compared all these three methods, and they're going to show us the data. So this is the result. Note that this is an ImageNet 10 shot accuracy. So take it with a grain of salt because it may behave differently on different data sets. What the author found out is they compared the absolute coordinates, which is 1, 2, 3, 4, 5, 6. It seems like it's working not too bad, just working fine. And the fractional coordinates that we just talked about, the maxing out to 100%. And they added one Fourier method. The Fourier method is basically a little bit like the sinusoidal encoding we've seen in the traditional transformers, but with the coefficients to be learned. I think this is first used in NERF papers. And in this work, the most performant is actually the factorized method over here. I think it's at 64.9%. So this is the best method that they found out. I say keep this with a grain of salt because the first thing they studied is actually the effect of resizing the image. Well, if we resize the image area to be quite small, let's say a quarter of the original size, what will happen? it seems like the model accuracy is actually pretty steady. Even if when we're dropping, of course, the bigger model is more accurate than the smaller model, but I think it's pretty steady. Even when we're dropping to 50%, the accuracy is pretty well maintained, and only after that we're going to see a significant drop of the image. So it seems like we can, if we are concerned about the budget, we can actually do inference of the model after resizing. It's going to be very cheap. So another way of resizing the image is to make it smaller by dropping random tokens. If we do that, will that work equally well? Well, the authors did that experiment, and it seems like dropping random tokens to make the image area smaller is not a great way to keep the accuracy. Of course, the model can run faster, but the accuracy is significantly dropped. So this is all about resizing, to make it smaller. Well, can we actually make it larger artificially to make it work better? So the authors actually did that. What they did is they resized beyond the original 100% if it still fits the sequence length. They did a comparison. So they first did some experiments where they said we only resize to the, at most to the original resolution. I don't upscale the image to beyond its original resolution. And the other experiment is just, let's go ahead and linear interpolate and see what's going to happen. I don't know if it's linear, but they just did resizing using the off-the-shelf algorithm. And it seems like by resizing, which I don't think is adding information to the model, right, it's actually making the model infer much better. So I think that's a very interesting finding, to my surprise. I don't know why. If you have thoughts, guesses, please let me know. So, after taking a look at the ViViT and NaViT paper, I didn't forget why we get started. I'm trying to understand how Sora can use them, so I'll try to make a few guesses. Well, why guesses? Because unfortunately Sora is not open source, at least not yet. So I found this paper. It's called Sora, a review on background technology limitations and opportunities of large vision models. That is not published by the original Sora team. It's just by another research team that's trying to reverse engineer what Sora may have done. So this is the architecture they reverse engineered based on the Sora technical report. I think they referred to the latent diffusion model and they used their schematic and they replaced a few components. What we have been looking at here is we have a raw video and we can use the method we've been learning about the space-time patches to encode it. The technical report said they use some kind of VAE, maybe VQ VAE, to compress it into a latent space. And the authors of this review paper called them the clean latent. And then maybe they use some other methods like the transformers to convert them into latent space-time patches with more contextual information. After that, there's going to be a lot of things that's happening. First of all, we need to have a diffusion transformer to generate the videos and also want to control the video. Of course, there's just conditioning. Maybe we give prompts. GPT-4 helps us expand the prompt. And we have the clip style calculator to help us convert those embeddings between different spaces. And what we have been focusing on is pretty much this detail. This detail between the raw image, compress it to the clean latent, and from the clean latent to the latent space-time patches. Of course, there are a lot more information we haven't covered. And I'm probably going to conclude here. Thank you very much for spending all the time, it's more than 30 minutes, about my first note on machine learning on my own. And I'm trying to read fun, interesting papers. If you're interested, please let me know, leave a message, and let me also know what you're interested in reading. Maybe we're both interested in reading how they did the diffusion block. Thank you. Oh, I have a question slide. Please feel free to leave questions in the comment section. This is one of my cats. Her name is Luna. Let me know or let her know.